So hopefully as you finished the questions on the previous page, page 29, you noticed that the more rectangles we had, the closer to the true area your answer for the area ended up being. If you actually wanted to go back and check, just in case you didn't, hopefully you got that the value of the integral, which is the true area of the actual shape, is 76/3 or about 25.333. And as you looked at your three answers for your areas, you probably noticed they did get progressively closer to that value. The first area was way off, it was 44. The second area was still pretty far off, it was 34. And then the one we did together was 29.5. None of them were perfect, but you can at least tell that the more rectangles we created, the less wasted space we have, and the more we get an accurate approximation that we know gets us closer, not perfect, but closer to 29.333. Now, of course, the downside to doing these problems is that you probably realized it takes a lot of rectangles to be accurate. 8 was kind of pushing the boundaries of our own sanity, but beyond 8, we know that we still have all of this little excess space. The good news is the smaller and thinner we make our rectangles, the less excess space we have to deal with. The downside is that's more calculation that we have to do, more y coordinates we have to find, more multiplication that we have to do, more adding that we have to handle. So you can definitely tell that the drawback to the Riemann sum method is that it can get really tedious at the expense of accuracy. So you do have a pretty major trade-off to have to consider. Would you rather have a very easy area problem but a pretty crappy estimate, or a harder area problem with a better estimate? So therein lies the rub with Riemann sums, and that's something that we'll kind of talk about as we get further into the concept. For now, hopefully you did notice that the smaller, or I should say thinner, the rectangles, the less wasted space we have and the truer the approximation really is. So keeping that in mind, page 30 sort of takes into account the way the rectangles were drawn and why. In the previous page, it specifies in letter A, the rectangles in those diagrams were called right-hand rectangles. And I sort of alluded to the reason in my wording in the previous video, but you might not have necessarily picked up on it. The height of each rectangle was dictated by this point that was touching the curve, happened to be the y coordinate of the point on the curve. But more importantly, every single rectangle, not coincidentally, was based on the right-hand edge. Notice each of those rectangles touched the curve on its right-hand edge. The left edge was just kind of doing its own thing, but we didn't even pay attention to the left edge because the height of the rectangle really is the same at both the left and the right edges, but it was the right-hand edge that we had information about. It was the right-hand edge we could use the equation to help us predict the y coordinate of, which told us how tall it was. So it's named a right-hand rectangle basically because the right edge of the rectangles literally touch the curve itself. Now, for that reason, you can probably infer in letter B that left-hand rectangles must have a similar significance. A left-hand rectangle is essentially just the opposite, where the left edge of the rectangle is going to touch the points on the curve. So I'm going to demonstrate how to draw left-hand rectangles with one of these diagrams. And then again, I'm going to give you a little bit of an independent task and ask you to see if you can do some of these things a little bit more on your own. So in letter B, I'm going to do the middle example for rectangles because that's kind of a happy medium there. Now, depending on whether you want the right or the left edges of the rectangles to be the ones touching the curve, that's going to kind of dictate the choices that we make. So if I want to start with a left-hand rectangle, this first point on the left is going to dictate the height of my first rectangle. Now, if you remember, I want to create 4 rectangles here, which means that naturally these tick marks, 1, 2, 3, and 4, should pretty well dictate the width of my rectangle. Now, if the left-hand corner of the rectangle is the one that's meant to touch the curve, then that means I can draw a quick little line here and and down. And that looks like it should suffice to be my first rectangle. Now you're probably noticing, and I'll zoom into it really closely so you can see it, you're probably noticing there's definitely another aspect of wasted space here. This time, instead of having too much area, you can tell we almost don't have enough area. By using this left-hand endpoint here, the height of the rectangle isn't quite tall enough to sufficiently fill in the edge of that space between the curve and the rectangle itself. But again, there's the difficulty with Riemann sums. We're trying to, as the old cliche says, fit a square peg into a round hole. We're trying to use a rectangular shape to approximate a curvy area. So we know there's going to be wasted space in some way. In the previous example, you saw wasted positive space looks like, where you have too much area. And in this example, you're going to see some wasted negative space, meaning some area that we're just not going to be able to capture with straight lines alone. So I'm going to kind of show you my technique for these things, and then you hopefully can kind of come up with a style for yourself. The way I'm going to do my rectangles is basically by doing heights first, and then I'll just kind of drop down the rest of it. So the next height is going to be based on this point at 1. I know it's going to be exactly 1 unit wide, and again, you can freehand it, especially if you just have a small little space to create. So once I draw that rectangle and I know how tall it's going to be, I'm just going to drop the height straight down. Now, of course, I'll go back afterwards and kind of box in my rectangles to make it look a little bit more precise, but you can usually do that little left edge at the end. Once you kind of know how tall it needs to be, that's the important part. So my next rectangle needs to have a left endpoint here at 2, so I'm going to draw across and then down. And again, once you kind of have a rough idea of it, then you can make that last one. Obviously, you can use a ruler, but I find that sometimes the ruler kind of blocks the points. So just for ease of camera work, I'm not going to make very straight lines, but hopefully yours will look a little bit better than this. And then we'll do the next one. At the next one, again, it needs to be 1 unit wide, and then I'll drop the height straight down. And of course, once I can make it look like a proper rectangle, ooh, that's worse zoomed in. We'll just zoom out and pretend it's a little, oh no, it's just as bad, isn't it? Well, all right, artistic liberties, we'll call them. But now that you can hopefully kind of see the 4 rectangles, we can get a better sense of what we're calculating. Shading certainly covers a myriad of sins. Instant masterpiece. All right, so my jaunty little rectangles here are complete, but you probably felt like there was a bit of unfinished business because of this little dot at the top. This will actually be one of the follow-up questions. It's actually question number 2, letter E, because there is supposed to be an unused point. You might not have noticed it, but even on the previous page, there was an unused point that we never ended up using as an actual vertex or corner of one of our rectangles. But nevertheless, that is supposed to happen. So I'm going to ask you to kind of hold off judgments on why exactly that is right now, because I do want you to try the other 2 diagrams. Try to practice creating 2 rectangles and then 8 rectangles so that you can see if there's kind of a theme or a pattern to which dot ends up going unused. And perhaps once you realize why that dot is unused, it'll make a bit more sense. Now, after you finish drawing your rectangles, the next order of business is finding their areas. That's going to come in question letter D. So when you do question letter D, it's just like we did on page 29. You're going to find the base and the height of each rectangle, multiply to find each area, and then find the sum of all of your areas. So the nice thing is this one's a little bit easier than the previous one in that the x coordinates are 1, or the spacing between the x coordinates is 1, which means the bases of each rectangle are 1. We are just responsible for finding the heights. Now again, it's the same y coordinates as the previous table that we created on page 29. So if you still have that screenshot, or if you want to go back to the previous video and pause it again when we had the calculator table on the screen, that might help, because we still know the y coordinates of all these spots. For example, 0 had a y coordinate of 1, 1 had a y coordinate of 2, 2 had a y coordinate of 5, 3 had a y coordinate of 10, and 4 had a y coordinate of 17. Now, of course, you don't need a graphing calculator. You can just as easily plug in these points into the equation. Remember, the equation was x squared plus 1, and you can get the y coordinates that way too. But for reference, if you want to use the table just to make things easier, you definitely can. I'll just quickly kind of summarize this area bit just so we can get that going. This first rectangle is a base of 1, height of 1, so 1 times 1 would be 1. The second rectangle has a base of 1, height of 2. 1 times 2 would be 2. The third rectangle has a base of 1, height of 5. Base times height would be 5. And the last rectangle has a base of 1, height of 10. So base times height would be 10. The sum is all 4 of those areas just added up, which looks like it'll give me 18. So for comparison, we don't really know how accurate 18 is, but we can definitely tell that it does not seem to fill in the entire space under the curve, so it's safe to say that 18 is probably not a very accurate answer. And once we see what the other diagrams will look like, we may have a little bit more context to see where 18 fits in the big scheme of things. So for now, see if you can try to finish as much of page 30 as you can with a series of observations / calculations. Practice drawing the rectangles, just so that way you can kind of get the hang of the technique, and then find the areas of each rectangle, which should be pretty easy. But use a calculator, especially for the 8 rectangle set, because the numbers are a little bit unwieldy. After you've made your diagrams, then consider answering the questions just based on your observations. For example, in letter C, they're throwing in some vocabulary that's very common in calculus, under approximations or over approximations. So that might be something to consider, especially in contrast with the ones you saw on page 29. And in question letter E, you'll see the question to which I was referring earlier in this video, the idea of the unused point. What is the deal with the unused point? Why is there an unused point? And how exactly will that affect our calculations, or will it not at all? It's just worth thinking about. In any case, use the answer key to check your answers as you go, and then once you're ready to do so, we will join up again in the video for page 31, where we'll try to kind of summarize your observations up to this point.